with their career. So today our experiment will be uh, understanding Hilbert transform and trying to use it to obtain instantaneous amplitude, instantaneous phase and instantaneous frequency of a certain set of signals, and let's see if we are able to see something interesting into it. Okay, so a brief note on Hilbert transform. So Hilbert transform is basically convolution of your original signal by 1 by t. Okay, so this is done so that your signal is quadrature phase shifted. Now, why it is done? Because your quadrature phase shifted signal is going to be orthogonal to your original signal. It's just like creating cosine signal out of a sine signal. Okay. Now, having briefly understood this, Hilbert transform is achieved by two ways. One, a simple convolution that I just explained to you, or you can perform Fourier transform and try to change properties over there. So in my case, I have an amplitude modulated signal, a frequency modulated signal, a power line signal, and exponentially decaying signal. So let us see if we can try to see an instantaneous amplitude in an AM modulated signal and see whether we get a message out of it or not. Okay, so to perform this, I have created a MATLAB function named okay, so I have created a MATLAB function named experiment 6am. Basically that's our experiment number that I am doing. Okay, so I have generated an amplitude modulated wave from expressions am is equals to c star 1 plus 0.5x, where 0.5 is my modulation factor. Okay, c is going to be our carrier. C is basically our carrier frequency wave, which is at 80 hertz, and x which is our message, is going to be around 8 hertz. Okay, now in my case, I have performed Hilbert transform using basically Fourier transform method, in which basically now we need to understand here that we are having discrete time sequence, right? As in MATLAB, this vector is going to be of discrete values. Okay, having understood that, what we can perform is discrete Fourier transform, right? After that, which is basically again is my own written function given in this way, which basically performs your discrete Fourier transform, followed by an Hilbert transform. Hilbert transform required changes that you need to do so that you get an effect of convolution with 1 by t, which is achieved using this way. So okay, so just let me show you. Right. Okay, so as you can see, what we do is, for signals, I mean in the DFT sequence, for the coefficients of k belonging to 1 is to n by 2, if n is even, we multiply all those coefficients with minus 1j, right? And for rest of the coefficients we multiply 1j. Okay, so this is basically nothing but convolution with 1 by t or 1 by n in case of your discrete time sequence. So if n is odd, rules slightly change, but the concept is same, that 1 is to n by 2, that means half of your Fourier coefficients that you estimate out of DFT are multiplied with minus 1j, while the rest of them are multiplied with 1j. Basically, the frequencies that get mentioned in 1 is to n minus 1 by 2 coefficients, those are called as positive frequencies, while the rest of the ones are called as negative frequencies. All right. So having basically understood what's happening inside, let us see if we are able to extract our message out of an amplitude modulated signal. Alright, so this is my experiment 6am. Let's see if we are able to get plots. Okay, so here we have our plots. I'll explain you all of them one by one. Alright, so this is our amplitude modulated signal. The one in orange you can see is the amplitude modulated signal, while the blue one is our original message signal, which is a simple sinusoid that I have imbibed on a carrier wave. Now to tell you that Hilbert transform performs quadrature phase shifting operation. As you can see, the orange color wave is basically computed by out of Hilbert transform, and you can see that the wave is slightly offset or shifted by some value as compared to your original signal, which is in blue color. Okay, now instantaneous amplitude is once a quadrature phase shifted signal is achieved, it is taken as this way. Of course, to achieve this quadrature phase shifted signal, after the DFT sequence and modification in DFT sequence, you need to perform an IDFT. Okay, so that gives you a time based sequence. Now to this time based sequence, you multiply a complex number j and then make another complex variable called z, which is nothing but your original signal plus your j into quadrature phase shifted signal, which is to say that it's something like cos of x cos of t plus j sine of t. That way you are able to create a complex number. Okay, having done that, the amplitude of the wave is nothing but simply square root of real part square plus imaginary part square, which is going to be your amplitude. So that you can calculate as like this. Okay, right, as you can see here, am is nothing but am dot am is basically the your original signal square plus 1 the quadrature phase shifted signal square, and you are performing a square root operation onto it. So that way you are going to get magnitude, and you can see that magnitude which we compute. Alright, just let me show. Yes, magnitude that we compute. So my orange color signal is my original message signal, while the blue colored signal is the one that I've computed from Hilbert transform. As you can see, this is basically the blue color thing, which is an instantaneous amplitude, quite closely follows up with the original message signal except for certain scaling factor. Right, so this was the application of Hilbert transform to see instantaneous amplitude and perform demodulation in case of an amplitude modulated signal. So let us see if we can try to do anything in frequency modulation. As stated earlier, given a complex number x plus jy, the phase of that complex number can be defined as tan inverse of y by x, right? So we perform the same thing in case of signals. Now that we have a quadrature phase shifted signal, which is basically orthogonal, or like y in case of x plus jy, the angle of this signal or the phase of this signal can be determined as the ratio of your quadrature phase shifted signal to that of your original signal, and you take a tan inverse of it. So in my case, I have implemented that in this way. So you see this expression over there, here is the frequency modulated wave signal generation. The x of t is your original message signal, which is around 8 Hertz. Your carrier frequency is around 80 Hertz. So this is the frequency modulated wave out here, right? Now again I have used have implemented Hilbert transform using Fourier transform method. Okay, so this Zn here is the complex number, which is going to be nothing but your FM, the original FM frequency modulated signal, into J times your quadrature phase shifted modulated signal, and when you are going to perform an angle FM, you are going to obtain the phase of this complex variable, which is the phase, which is basically this part of our equation. Now that we know this, what we have to do to find out instantaneous frequency is differentiate it, right? That's why I've used the function diff. Of course, one has to remember that the number of points get reduced when you use a diff operation by 1 unit, right? So let's see if you are able to get this code working. Okay, so here we are with our results. So this is the quadrature phase shifted, I mean you see the orange colored signal is the quadrature phase shifted signal. As you can see, where the sinusoid gets lower in frequency, it automatically also changes your phase shift, so that these two signal parts are again quadrature phase shifted. Similarly, even if as you reduce the frequency, it also reduces the delay for you, so that the quadrature phase shift part is retained in entirety of the signal. Okay, so now that we have done that, all we have to do is perform obtain phase of the signal. Well, by the way, this is our frequency modulated signal. So if you perform FM demodulation using the method I have mentioned, like differentiate and unwrap an angle of your complex number estimated out of your signal. So you can see my orange colored signal is basically my message signal, while the blue colored one is the one I have demodulated and found out using Hilbert transform. As you can see, it also closely follows up your message signal, except for certain computation errors that you cannot avoid, right? So these glitches you can see over here are some, one can think of it as a floating point errors also, right? So having discussed these techniques, so today now I would like to show you the same kind of analysis over power line signal as well as exponential signal. Well, as for exponential signals, I have created a report over here, and one can see, so this is my exponential signal. As you can see, the amplitude is quite dying, is exponentially decaying, while there is a high frequency varying sinusoid in between. All right, so you can see using inbuilt functions IDFT and DFT, I have created here I have estimated instantaneous amplitude, and the orange colored curve that you can see is basically the Hilbert my implementation of Hilbert transform, while the blue colored curve is the Hilbert transform from the MATLAB itself. Well, while plotting, I have kept a certain scaling factor so that the curves can be visibly separated. Okay, although in reality these two curves are the same, right? The phase response for exponentially decaying signal is quite linear in nature, and the two curves, basically my version of Hilbert transform and MATLAB's inbuilt function Hilbert, overlap, and basically they indicate that my code's working really. The frequency is some constant value, you can see just above 1. Of course, again, then I have kept a certain scaling and DC factor so that the two signals, that is the one generated from my Hilbert transform as well as the inbuilt Hilbert transform, are separated. The curves are really the same, right? So now I will show you a live demonstration for a power line signal. One needs to understand that a power line signal has issues of slack and swell, meaning that the amplitude of the signal does not remain constant. We expect it to be 50 Hz to 60 Hz with some constant voltage of 220 volt RMS, right? However, that does not remain the same as the loading onto the circuit, loading onto the plugs and switches changes over the time. We find certain slack and swell of the signal. What I mean by that is, I'll just show you now. So I have created a HBT plot which basically is going to perform DFT and then IDFT based method for Hilbert transform. Of course, I have also used MATLAB's inbuilt function Hilbert, and I'll be basically comparing them in using phase plots, frequency magnitude plots, as well as frequency plots, right? So let's see if we are able to perform. Let's know the name HBT plot, right? So HBT plot, and my signal is basically power line signal here. I'm giving one row of it. Okay, so one thing to be noted is, if if you are using DFT and IDFT, since the order of its the implementation is such that it's of order of n square, it will take quite a long time if your data is too large, such as in my case. The data length is 4801, so it is going to take quite a lot of time for the computer to perform the DFT and get the matrix, get the outputs. However, one can always use FFT and IFFT, so that is basically the same implementation of DFT. However, the order is of log n, so you'll find a faster implementation of it. Okay, so here we are with the plots. I'll explain each of them. Okay, so this plot you see is our power line signal, which is basically a 50 Hz signal. As you can see, the amplitude is suddenly shifting and then suddenly dropping also. So this shift or increase in amplitude of the wave suddenly is called swell of the signal, while suddenly drop like this, suddenly drop of the signal is called as slack. So okay, so you can visualize it here. Now, using instantaneous amplitude calculation that I mentioned earlier, we will try to see if we are able to detect our slack and swell into the signal. Alright, so in my case I have computed instantaneous phase and amplitude. I'll show all these plots one by one. Right. Okay, so this plot is of instantaneous amplitude. As you can see, there is a sudden increase in amplitude, which is seen as the swell in the signal, and then the fall bits in the signal is basically the slack of the signal. I've compared here my two results. One of the curve is from my built Hilbert transform function, and the blue colored one is basically from the Hilbert transform function itself. As you can see, the two curves really match well except for certain scaling factor. Okay, right. If you try to see the phase response, okay, so you see the phase response is linear. This is quite expected as your frequency of the signal is constant, so your phase is going to be nothing but omega t itself, or something that is linearly dependent upon time. Right, the slope of this curve, if you estimate, is going to be your frequency itself. Now the frequency of the curve, frequency of the two, you can see like this. So as you can see, basically the orange one is again the computed from Hilbert transform, that is input function, while the blue colored one is mine implemented version. To see that there is a slight variation in frequency, which is quite unnoticed in case of our signal. From here, looking here, we cannot really say whether there are frequency variations or not, but whenever there are certain slack and swell issues, you can see that there are certain spikes you observe. These are going to occur because sudden changes in your amplitudes indicates presence of high frequency components. Of course, they do not die down, and this variation in frequency you can see is basically indication of noise. This part of signal tells that there is a lot of noise involved in the frequency variations, although all of which are very, very minute and may not be visible in our signal like this. Okay, so with this we come to an end of this session. Hope you enjoyed the video. Thank you.